Hey everyone, this lecture we're going to be talking about metamorphic rocks. So we've already chatted about igneous rocks and sedimentary rocks, so let's learn about how metamorphic rocks are formed. In this lecture, we're going to be talking about metamorphism, and some of the high-level learning objectives is that metamorphism is caused by changes in temperature, pressure, and stress. Metamorphism alters the texture and mineral content of rocks. It's associated with plate tectonics, of course, and we can classify and describe metamorphic rocks. So what's metamorphism? A metamorphic rock is one that's formed when a pre-existing rock, which we call a protolith, undergoes a solid state change in response to some modification of its environment. An example of this is the metamorphism of a caterpillar into a butterfly, and that changes because of things that happen in its environment. So we see metamorphism of rocks through changes of temperature, pressure, and stress. So like I said, what a protolith is, that's basically the original rock. And this original rock can then undergo pressure and stress and heat, and that causes the original rock to be metamorphed into something else. So an example of that, let me take away my face. An example of that is you start with red shale, the protolith is a shale, and then that gets metamorphized into a gneiss. And we have here in this bottom picture, we have a sedimentary rock that has fossil fragments, and then that gets metamorphosed into those fossil fragments then become calcite crystals. So again, the protolith is the original rock that is then changed through heat and temperature into something new. And generally speaking, the metamorphic rock looks very different than the original rock. So let's have a demonstration of what that looks like. And I'm going to use some pieces of candy to try and demonstrate how a metamorphic rock is created. Let's take a look.
In this demonstration, I'm going to use candies to demonstrate metamorphism. So, in order to have a metamorphic rock be created, we need heat and pressure. So with these candies here, we're going to simulate that each of these little candies could represent individual mineral grains, maybe a sedimentary rock, or maybe an igneous rock here. And we're going to apply some heat and pressure.
A few moments later.
Ooh, yeah, that's soft. I think we're ready. All right, I got my bowl of warm rocks here. We have a mixture of minerals and some igneous rocks and sedimentary rocks. So now that was the heat that was applied. Hot. Oh, that's hot. Okay. And now we're going to apply some pressure. Okay, I didn't know what I expect here. Here we go, apply some pressure, and we're just gonna keep applying pressure because at greater depths in the subsurface, there is immense amount of heat and pressure. You can see that the heat has made this quite elastic and gooey. And if we keep applying pressure here, we can see that what we end up with is quite a mixture of candies here. So if we remember what the original candies look like, here's some of the original candies. And now you can see that over some time here of having applied pressure and temperature, you can see now that we have a lot of stretching that's happened, layering, and you can still kind of see a little bit of maybe the original rock, but you also see it in a completely different state. And so this this candy mess here represents a metamorphic rock.
Like I showed in that example, we have different textures and different layers that are associated with metamorphic rocks that are definitely distinct from other types of rock. And we describe that with the word foliation. And foliation is layering that occurs when these mineral grains lie parallel to one another and elongate mineral grains are aligned with one another, or the rock displays alternating light colored and dark colored layers. So foliation, again, is referring to these layers that occur within a metamorphic rock. And of course, we have metamorphic rocks that are not foliated. So we're going to talk about foliation versus non-foliation a little bit later in the lecture. So there are some processes that occur during metamorphism. We have things like recrystallization, phase change, metamorphic reaction or non-recrystallization, pressure solution, and plastic deformation. So let's talk about what all these mean. Okay, in recrystallization, this is where changes in shape and size of grains occur without changing the identity of the mineral. So an example of this is here's our protolith, which has our original rock, has very tiny, small clasts. And then as it undergoes metamorphism, those it creates crystals, and these new grains are very large. So we go from a tiny clast to a really big clast. This phase change, which transforms one mineral into another mineral with the same composition, but a very different crystal structure. So at this small scale, these phase changes involves the rearrangement of those atoms. Okay, a metamorphic reaction or recrystallization is a result in growth of new minerals that differ from those of the protolith. So during recrystallization, we have a chemical reaction that effectively digests minerals of the protolith so that the chemicals can go into production of new minerals. So we have clay and quartz here in our protolith. Now there's a chemical reaction that occurs, and during metamorphism, we result in quartz, garnet, and mica. So some of these do resemble the protolith, but they undergo this recrystallization as a result of a chemical reaction. Pressure solution. This happens where the surface of one mineral grain pushes against the surface of another, and under those conditions that allow water film to exist between the grains, this is where we get a pressure solution under metamorphic conditions. So the grains preferentially dissolve. So they dissolve in one direction and at the surface contact, and then that results in these ions of fluids, for example. They can precipitate and they can push along the sides of the grains. So, for example, here's a picture of our protolith where we have spherical grains, and then as it undergoes pressure, this pressure solution dissolves the grains and they have a preferential direction. And so now we get elliptical shaped grains. And you can see here that there's a distinct direction in which fluid would want to flow. And this is where we see things like foliation. In plastic deformation, this occurs when a rock becomes warm enough to behave like a soft plastic, so that minerals can change the shape without breaking the grains. So again, if we were to start with spherical grains in our protolith, and then due to heat, we get plastic deformation into elongated or elliptical shaped grains. Again, this is a result of typically high temperatures or shearing stress. So we get metamorphism due to heat. Heat causes the atoms to vibrate rapidly, they stretch and bend, and as they cool, it locks the atoms into a different orientation. And if the bonds stretch too far and break, these atoms can detach from their original neighbors and they form new bonds. So you could think about metamorphism sort of like making a box of mac and cheese. The dish is made up of totally different ingredients, like individual grains or different types of rocks that are then heated. They're boiled and mixed together and baked into something new. So an example, if you think about metamorphic rocks, is either smushing those candy pieces together or maybe something like mac and cheese. We also have metamorphism due to pressure. So near the Earth's surface, minerals with relatively open crystal structures can be stable. But if you subject those minerals to extreme pressure, they get packed more closely together and denser materials tend to form. So these transformations can take place during phase changes and during what we call neocrystallization. So if you have metamorphism due to pressure, you may have experienced pressure yourself if you're diving into a pool, or if you've taken a flight in an airplane, you yourself have experienced those pressures, and maybe you feel like you're under more stress when you're in the air a few thousand feet. So when we have changes in both pressure and temperature, we can express that in what we call a geothermal gradient. And this is something that we see in the subsurface. So the plot here on the right is a general geothermal gradient of the subsurface. We can see that it's linear, and that these different gradients affect different types of rocks at different slopes. So there are different rocks that occur at 15 kilometers below the Earth's surface, then they occur at 30 kilometers below the surface, and that's due to the geothermal gradient. So the hotter it is and the deeper it is below the surface, the different types of metamorphism can occur. Let me move my face. Okay. So we also have stress and preferred orientation. So I talked a little bit about that before, but we have different types of stress that occurs in the subsurface. And we'll go into this a little bit more in the structural geology lecture. We have tension, which is pulling apart, compression, which is pushing together, and we have shear stress, which is side by side. Or if you were to, it would basically cause a block to rotate. So these stresses can be applied in different directions. And stress causes preferred orientation. Okay, so let's grab your sheets and watch this YouTube video. And don't forget to fill out that last part about metamorphic rocks.
All right, in this video, we're going to be talking about metamorphic rocks. Please get your rocks flowcharts ready so we can fill in our final third column. Now, recall, rocks are classified according to how they form. Igneous form from cooling and solidified magma. Sedimentary form from compacted and cemented sediments. And now our metamorphic rocks, these are ones that are going to undergo some sort of change, a metamorphosis. And what drives that change is exposure to heat, really intense heat, or pressure, intense pressure. So metamorphic rocks are rocks that are changed as a result of exposure to intense heat and or pressure. So there are two types of metamorphism that occur in nature. And the first type is called contact metamorphism, and the second is called regional metamorphism. So let's talk a little bit about the difference between these two. Now, imagine you have the surface of the Earth here, and you can see some trees, and these colors here, these are layers of rock underground. And so I'm going to show you how contact metamorphism works. The reason it's called contact is because it involves existing rocks coming into contact with really intense heat, which is generally provided by lava or magma. So imagine that one day an intrusion of magma forces its way up through these layers of rock. Now, all of the existing rock are going to be burned by the heat of the magma. So all along the edge of this magma, shown here in orange, you're going to have rocks that have been burned by the heat of the magma. That burning causes them to change or metamorphosize into something new. So anywhere you see the orange, you're going to have some metamorphic rock. This is caused primarily by heat. Let's fill this in on our flowchart. Okay, so the first type is contact metamorphism, and this is caused by contact with heat. Whenever a rock comes into contact with magma or lava, it is burned or metamorphosized by that heat. But let's talk about the second type, regional metamorphism. Now this one is going to be more from pressure. So let's imagine that I have a plate boundary here, a fault, a crack, and that these two plates are coming together. So it's a convergent plate boundary. Well, as you can imagine, in the middle here, there's going to be immense pressure, and that pressure can cause the rocks trapped in the middle to become metamorphosized. So all along this boundary, you'll find metamorphic rocks. Again, this is different from contact in that it's not so much about the heat, it's more about the pressure. Let's take a look at what we see here. This is a typical progression of metamorphism that occurs, starting with the sedimentary rock shale. If you add heat and pressure, it will metamorphosize to slate. If you add more heat and pressure, it will become phyllite, more, and it will become schist, even more, and it will become the metamorphic rock gneiss. Take a look at that gneiss sample down there. You'll notice it has bands of minerals. That's a result of the intense pressure. Now, if you were to take gneiss and add additional heat and pressure, it would likely melt into magma or lava, and then it would become an igneous rock. So gneiss is generally the extent of metamorphism that we see. Let's go back to our flowchart. So our second type of metamorphism is called regional metamorphism, and this is caused primarily by pressure. Of course, all of this is summarized in your reference tables on the metamorphic rock chart on page 7. You'll notice type of metamorphism, composition, what minerals are involved, how big the crystals are, whether it has banding or not, the names of the rock, and the map symbols. And of course, we'll learn lots more about this chart in detail in the coming days. Thanks for listening.
All right, so we can differentiate metamorphic rocks into basically two fundamental groups, foliated and non-foliated. So I talked a little bit about that texture before. So now let's look at some examples. So foliation refers to the parallel surfaces or layers that can occur. And foliation can be distinguished by things like its composition, grain size, and the nature in which it has created its foliation. So some examples of metamorphic rocks with foliation include slate, phyllite, schist, metaconglomerate, gneiss, and migmatite. So here's an example of phyllite. During the formation of phyllite, we have clay that recrystallizes to form tiny mica flakes. So if you remember when we talked about mica in the minerals section, you may remember the picture where you could see those sheets of mica flakes. And so when it undergoes metamorphism, phyllite still has that same foliation characteristic. Here's an example of a metaconglomerate. And so in a metaconglomerate, pebbles and cobbles flatten into a pancake. So this is where we see those, what used to be a circular grain now has been squeezed, and now it's elongated, and it has this ellipse or elongated shape to it. And here's a diagram of how we get foliation, and in a larger scale, how we can see foliation, not just at this size, which is, here's the size of a coin. So if we're looking at a rock, these are scalable, foliations within a few feet. But what about larger picture? So here's an example of how we can get foliation with much larger outcrops. So we have, in this example, over time, we have shear stress that has been applied. So what started as these mafic components of something that looks a little bit angular shaped grains, as shear stress is applied, as it gets rotated and pushed together, this is where we see some foliation. And these once darker looking mafic components here are then stretched and elongated. And this is how we see some of those very distinct foliation patterns in a larger scale. And then, of course, when we look at an example of gneiss, we see that the original rock here, we see a mixture of felsic and mafic materials together. And as these minerals dissolve, the ions then migrate into this these preferential zones, which then creates these foliations, and therefore we get separating of bands. We get the banding effect here of darker colored mafic bands and lighter colored felsic bands. So what about non-foliated metamorphic rocks? These are rocks that contain minerals that recrystallize or grew during metamorphism, but they don't necessarily have that preferred orientation. So some examples of that would be hornfels, quartzite, and marble. So here's an example of quartzite, which is the original rock is sandstone, quartz sandstone, and then it just undergoes more metamorphism. And so the recrystallization or grains have changed once the heat and pressure has been applied. So I talked a little bit about this before with the pressure and temperature gradient, and different rocks occur at different temperatures due to the metamorphic intensity. So we can describe how intense metamorphism is through these grades. So a metamorphic grade refers to the intensity of the metamorphism or the degree of metamorphism. And this is mostly dependent on temperature. So at low grades, we would have less recrystallization. And then at high grades, we would have increased recrystallization. So again, at higher temperatures, we tend to produce coarser grains and new mineral assemblages that are typically more stable at high temperatures and pressures. Here's another example of metamorphic rocks, their grades and mineral composition. So here we have clays and quartz that have individual beddings. And as we increase our metamorphic grade, you can see that we see things like slate and metasandstone. And at even higher grades, we see things like phyllite and quartzite. And when we have foliation occurring, this is where we see things like schist and gneiss. So these are some examples of rocks that we see at lower grade metamorphism to higher grade metamorphism. So gneiss would be an example of a high grade. Schist is an intermediate grade. So is phyllite and quartzite, and a low grade would be slate and sandstone and some shales. So where does metamorphism occur? Everything always comes back to plate tectonics. So metamorphism can occur in a few different ways. We have thermal contact metamorphism, which applies heat without change in pressure. And these are typically found near igneous intrusions where we have really, really, really high heat, but no pressure differences. So we might see this near, an igneous pluton or like a dike or something like that. And this is where we get metamorphic rocks right close to this intrusion. We have other things like burial metamorphism. This is where sediment undergoes burial in subsiding sedimentary basin. We have the temperature and pressure that increases, and then the metamorphism ultimately occurs due to it being buried. This is where we have, like in plate tectonic setting, we have subductions and things like that. So we have rocks that are being buried, and we have sediment that's the overburden is putting pressure, and then as the rocks get buried deeper, they undergo metamorphism. Okay, dynamic metamorphism. So at very high temperatures, like at great depths near a fault zone, we have the recrystallization that occurs. And these typically occur during shear stress environments. So if we're near a fault and we have this shear zone right in between where we have extreme temperatures is where we would see recrystallization. So dynamothermal or regional metamorphism is metamorphism that affects a large region, such as the creation of an entire mountain range in a subduction zone. So this is where we have the entire zone, it heats up due to geothermal gradient or igneous activity. Then we have the great pressure of an overburden. And then as it gets buried, it can undergo stress like compression or shearing. So if we start at point A here at the surface, and if we're near a subduction zone, this gets buried and there's overburden on top of it. And over time, as it gets buried at greater depth, there's greater pressures there, and this is where we get regional metamorphism. Okay, hydrothermal metamorphism can occur at mid-ocean ridges, and this is where we get hot magma rises beneath the axis of the mid-ocean ridge, and then it's exposed to seawater. The fluid is transformed into hydrothermal fluid as it rises through the crust. So this has to do with the influence of seawater as it forms and cools. Metamorphism in subduction zones, this occurs due to the extreme pressure caused by the weight of the overburden. And like I said, we have compression and shearing stress that can also take place, and that would cause metamorphism. Move my face. Okay, so exhumation and exposure of metamorphic rocks. How do we get metamorphic rocks at the surface of the earth if it's been pushed down and buried and it requires extreme temperature and heat and pressure? We don't see that at the surface of the earth. So why do we see metamorphic rocks at the surface of the earth? So two continents push together, and those rocks, as they squeeze together, can be pushed upwards. So that picture here in the top right is an example of where we have two continents, for example. As they push together and squeeze, the rocks would be pushed upward. We have an example of, say, a mountain range grows, and the crust at the depth beneath it warms up and becomes soft and weak. And as the range starts to collapse under its weight, the crust spreads laterally. And then, of course, we have erosion that takes place at the surface. So this whole exposure of metamorphic rocks plays into the rock cycle. So imagine that we have these continents that push together, squeeze the rock up, and it creates these rocks that were buried very deeply below the surface up to the surface, and rocks at depth become softened. And the example that I found here is that imagine it being like a block of cheese and how it melts in the sun. And then, of course, once we have metamorphic rocks at the surface, then other processes can take place like erosion. Okay, so here's that temperature gradient again, a little bit larger. So let's talk about it a little bit more. So remember I said that metamorphism can occur in different grades. We talked about contact metamorphism. We talked about regional or mountain belt metamorphism. And at these different temperature gradients and depth gradients is where we see metamorphism of different rocks. So at roughly where this line is dashed, that's where granite starts to melt. And at this dashed line, that's where basalt starts to melt. So you can see how basalt can withstand much higher temperatures than some other rocks. Okay, so in summary, we learned a lot about metamorphic rocks. Metamorphism refers to changes in a rock due to temperature, pressure, and stress. or the interaction with hydrothermal fluids. Metamorphism involves recrystallization, phase changes, metamorphic reactions, pressure solution, or plastic deformation. Metamorphic rocks can be classified as either foliated or non-foliated. Rocks form at different temperatures, and low grades generally correspond to lower temperatures. High grades generally correspond to higher temperatures. And of course, metamorphic rocks can be found at different places around the world based on the different pressure and temperature setting. We see that there's a correlation between metamorphic rocks with plate tectonics. And of course, we need things like plate tectonics in order for those metamorphic rocks to come to surface. So I'm going to leave you with just a few YouTube videos. Of course, as you watch more YouTube videos, it comes up with these suggestions. So this one's a pretty funny one. If you're looking for a laugh, I'll send that to you. And then also, there's this really interesting video about marble. So have you ever wondered where your marble countertops come from? And it might not just be something that you should think about in the context of learning about physical geology or learning about minerals and metamorphic rocks, but it's one of those things that you use every day. And maybe next time you go to a restaurant and wash your hands at the sink, you'll notice that it has a marble countertop. All right, that's it for this one. See you later.